Good evening, ladies and gentlemen. It's Wednesday night and it's physics night. We are starting with forces this evening. We have balanced and unbalanced forces, and we're going to look at Newton's second law, F equals ma, the mathematical treatment of it. So let's get started because there's a lot to go on in this. All right, so basically, in order to discuss forces, we're going to have to really start with the basics, what a force is and what they do. Okay, so forces run in the whole kind of end of things, that if you're a force, you are either pushing something, you are pulling something, or you are twisting something in some form of weird kind of Christmas type game, right? Push, pull, twist. Any of those things are attempting to happen, there's a force going on. Right? What do forces do? Forces will change the speed of an object, they will change the shape of an object, or they will change the direction of an object. Okay. Now, the important thing to notice here is that we have change appearing in all of those things. All right. So that's a little bit of a problem from the get-go, because there is not a single object anywhere in the universe that doesn't have a force acting on it. Everything has some form of force acting on it in some way or form. Okay, so what we need to understand is, how is it possible that there are things in the universe that are not changing speed, are not changing shape, and are not changing direction, but yet still have forces acting on them? Okay, so here's what we got. Let's imagine that somewhere in deep space we have a little circle, a little particle or a little planet or whatever, pick your scale. Right? And let's imagine that because of gravity, it's being pulled towards something else, and you can't escape gravity no matter where you are in the universe. So there's a force here, okay? And we'll call that a gravitational force. All right. Now, by this diagram, because there's a force acting on this object, it should be changing speed, shape, or direction. So in that case, this object should be traveling this way, and more than just traveling this way, it should be accelerating, because its speed should be changing. It can't just travel at a nice steady speed. It must be getting faster, and it's going to be getting faster in this direction, or it's getting slower, but it's getting slower in this direction. The only possible way that this thing cannot be changing speed, changing shape, or changing direction is if there's a force that is completely cancelling out that gravity force, okay, heading this way. Maybe it's the gravity due to some other object somewhere in the universe, so we'll call this gravity 2. And as a result, because these two things are exactly equal to each other and exactly in opposite directions, don't let the diagram fool you, they should be in opposite directions, then whatever effect happens this way is cancelled by whatever effect happens that way, and the result is that you have no change in speed. So what we actually should have here is, rather than forces change speed, change shape, or change direction, the key word here is forces try to change speed, they try to change shape, and they try to change direction. Whether or not they're successful is irrelevant. And in fact, depending on where you view it from, they may be successful and they may not, even with the same object. If you're super nerdy and you want a little bit of extra reading, look up inertial reference frames to have your mind completely blown about what you think of in terms of stationary. All right, now, critical point here. If you were to ask your average student what's going on in this diagram, they would say that this object is sitting still. It's being pulled this way as much as it's being pulled that way. And that is the biggest mistake that tends to happen at this stage. Okay? At this stage, the only thing you can say is that this object is not changing speed. All right, I'll say that one more time. When these two forces are balanced, the only thing that I can say is that this object is not changing speed. It may be that this object is in fact going like bejesus. Okay? It's just not getting any faster in the bejesus direction, and it's not getting any slower in the bejesus direction. All right? All we can say is that it's not changing speed. So if it is going really fast, it stays really fast. If it's going really slow, it stays really slow. And if it so happens to be at rest, it stays at rest. Okay? All we can say when we've got balanced forces is that there's nothing happening. There's nothing changing. It doesn't mean to say that it's not moving. That's got to help. Okay, got to get that. All right, so then what we do is we start applying some numbers to this. And usually this is done in a very boring kind of block diagram way. All right, in an actual exam, they'll have an art department that's going to makes piles of money out of it, does interesting little diagrams. You'll have a little question to start telling you about how Jeff has always wanted to water ski and he loves his water skis so much, and there'll be a nice picture of a water ski there. It's all irrelevant, okay? Fundamentally, it's a block diagram with some text to annoy you. Right? If I said that I've got 100 newtons this way, newtons being the measurement that we use for forces, and I've got 50 newtons this way, well, not use 50 because that's annoying. If I have 25 newtons this way, then we can make a couple of things about this. All right. The first thing I can say is that this object is changing speed. All right. That's number one. So this is changing speed. All right. It is changing speed in this direction, because this force is bigger. We don't say changing speed because we're clever at this channel. We can't use changing speed. People might think that they can do physics too if we use things like changing speed. So we give it a fancy name. We call this acceleration. Okay, and this is accelerating this way. Right. That's the best I can do. There's a massive temptation to say that this object is moving to the right. A huge temptation to say that. It just looks like it in the diagram. But that's not actually true, because what if I change this, and I'm going to try some really, 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 really dodgy art at the moment. Okay, so let's try and give it a couple of wheels. Okay, there's one of those moments where you go, can you tell what it is yet? Though that reference is dangerous. And let's pop a little front on this thing. Right, and a little window for the driver to look out of, and the back here, and there we go. Terrible art class. This is supposed to be the front. This thing may in fact be traveling this way. Okay, and then this force diagram takes on a whole new kind of life. What's this thing doing? It's slowing down. Okay. Or it's reversing. It's doing one of the two things, but let's assume that it's traveling this way to start with. This diagram then says that it's slowing down. All right? So it's now accelerating, but in a direction that is opposite to the motion. Now, it would be nice if we could just say it's accelerating in the direction opposite to motion, but because of the fact that that is actually something that's important to us in real life in day-to-day context, it's not just a physics idea, we then say that when an object is accelerating in the direction opposite to what it's moving, we call this deceleration. Okay? Or in the specification, it's referred to as retardation, okay, which is the slowing down of something. You're like en retard in French means late. Okay, so it's getting slower. Happy enough? And this is just language. Okay, accelerating in the opposite direction to what you're traveling in is deceleration. It pops out of your mathematics as a negative answer eventually. Okay. Happy enough with that. Remember from our motion one, if you had A equals V minus U over T, that if V was smaller than U, then you get a negative answer. And the negative answer for acceleration is deceleration. Okay? Right, so that's point one cleared up. Point two in this then is recognizing when things are balanced or imbalanced. So let's pop some arrows on here. So we've got an arrow out here, and we've got an arrow out here, and let's give you some simple forces here. So let's say this is 200 newtons this way, and 200 newtons this way. Right. No prizes for saying that these two forces are balanced. Okay, there's 200 newtons going one way, there's 200 newtons going the other way. The overall effective force acting in this object is nothing. This object is in fact indistinguishable from an object that has absolutely no forces acting on it. Okay, as far as physics is concerned, there's not much difference between the two. Okay, in terms of motion anyway, in terms of its acceleration. All right, so if that's true, we've got balanced forces. We can say that the overall force is equal to the total forces one way. Take away the totals forces, really? I know I'm Irish, but I'm not Irish. But yeah, I'm no. Anyway, right. Overall force, total force is one way, and then take away the total forces the opposite way. It's taking a new line. That's dirty looking. Okay, happy enough with that, everybody? I hope so, anyway. Now, we don't use overall force because, again, that would be far too accessible in terms of language. We use the word resultant force. And that needs an L. Okay, so the resultant force is equal to the total forces one way minus the total forces the opposite way. Okay, so what we mean by resultant force is we simply mean the overall force. Now, sometimes that's going to be straightforward. In this case, the resultant force is 0. Change these numbers ever so slightly, and I have, let's change that to 400. No, we'll change it to 500. We've got 500 to the left, 200 to the right. The resultant force is 300 newtons, but it's more than that, okay, because forces are vectors, so the direction is important. It's 300 newtons to the left. And since I know that there's an overall force of 300 newtons to the left, I can say that the acceleration of this object is this way. I cannot tell you which way it's moving. I have no idea about that. But I can tell you that it's accelerating this way, that its speed is changing in the left direction because that's the direction of the largest force. Okay? There are a couple of slightly more complicated versions of this, but it doesn't get much more complicated. Sometimes you have multiple forces acting, so maybe you've got a force there, and then a force this way. And let's go mental. Let's try one up this way and one down this way. All right, and let's whack some numbers in here. So let's put 40 newtons up this way, make this one 40 newtons as well, and we'll change that later to see what happens. 30 newtons this way. I'm using a lot of red here this evening. 5 newtons this way, and 8 newtons this way. Okay, so what can I say here? Well, what I have to do is I have to go which forces are going one way minus the forces the opposite way. I can't do anything with this 40 and 30 together, right? Because they're not going opposite to each other, or they're not going the same way as each other, so therefore they are just they're not interacting with each other. This 40 and this 40 are acting exactly opposite to each other, so in the up and down direction there's 0 newtons. So it's not moving upwards, or it's not accelerating in the upwards and downwards direction. I don't know if it's moving upwards and downwards, but I do know it's not accelerating in that direction. In the left to right kind of thing, I've got 5 and 8, which is 13 newtons to the left. I've got 30 newtons to the right, which gives me an overall force of 17 newtons to the right. So if I reduce this down to its simplest equivalent, this would be exactly the same as an identical object with simply 17 newtons to the right on it. And that's going to be really, really useful when you come to do calculations on this, because you can't put 5 forces into a single force equation. If we look at the left of the screen, you'll see that it's F equals ma. There's just one F there, so therefore it's just going to be one number that you put in. Now, if I had, instead of 40 newtons up here, I'd have 50 newtons up here, this becomes a lot more interesting, because I would then have 17 newtons to the right, and I would have 10 newtons upwards. Now, I only do this because you could get asked a written question about this. You would not get asked a calculation question based on this, but in this case, what you would be able to say is it's accelerating to the right and upwards. So it's going to be accelerating kind of in this direction here. Okay, not exactly diagonally, because it's slightly more to the right than it is upwards. So you're going to accelerate off kind of to the right and upwards. Now, for those of you that are doing further maths, and those of you planning to do physics next year, you can actually work this out, because this force and this force, you can stick that together like this. You can add them, and then you can draw a little line up like this, and you can use Pythagoras' theorem. It has a use to find out the size and direction of this force. But we're not going to do that this evening, because it's not on either the triple award or double award specifications to do that. All right. So that's kind of balanced and unbalanced forces. If forces are balanced if all the forces going one way are equal to all the forces going the other way, so your overall resultant force is 0. You generally are going to find yourself unbalanced in one direction or another direction, and you need to be able to kind of put that in and say, oh, that's going 17 newtons to the right, that's going 15 newtons to the left, so I know its speed's changing in that direction. Okay? So this brings us to kind of the pivotal part of forces, which is the force equation. And the force equation says that F equals ma. Let's play along at home. Let's see what these letters mean. All right, so we'll start with the easy one, that m is equal to mass. If you're on chat right now, stick what you think F is equal to and what A are equal to. You're 6 seconds behind me, but I'll go really slow with this. So m is the mass of the object. It's a measurement of how much stuff is in it. And that is measured in kilograms, and you have no choice here. You have no choice. This is not a wishy-washy equation where you can substitute whatever ones you want into it. You have to have mass, and it has to be in kilograms. No grams, no stone, no pounds, none of that. Mass, kilograms. A, if anybody's in the chat, let's have a look across. Oh dear, disappointing altogether. A is acceleration. Okay, and acceleration is measured in meters per second squared. Okay, so acceleration has to be measured in meters per second squared. No centimeters per second squared is allowed here. Common exam trick to do that. You have to convert that into meters per second squared. Which leaves us with F. Now, I don't like writing this equation as F equals ma. I prefer to write this as F subscript R equals ma, at least in the initial phases of getting this kind of learned into your head, because F subscript R stands for resultant force. Okay, and many a good student has come unstuck in this section because they've looked at a diagram, they've seen F, and they've just picked the forward force. Okay, you have to do your whole break it down into a single force thing first before you can use this in the equation. And this has to be measured in newtons. And because forces are measured in newtons and you have no choice in that, that's why kilograms and meters per second squared are required. Hello, Future Gamer Extreme, just seeing the message in chat there. Okay, so what's this? What do we do with this? Okay, so what we do with this is we then apply this to situations, and we're going to try and find resultant forces, and we're going to find acceleration, and we're going to find mass. If there's the odd person in the chat that's doing foundation tier, it used to be that you could only be asked to calculate the force. That has changed since the revision of the specification. You can be asked to rearrange this formula. If you're doing higher tier or you're doing triple award, be expected to have to rearrange this equation. It seems highly unlikely that they're going to give you a straightforward one. So let's start with an easy-ish example. Let's say we have an object with a single force acting upon it. This object has a mass of 20 kilograms and is accelerating in the direction of the force. It has to be, so we'll do a wee dotty arrow to show acceleration just so we don't get confused. And let's say it's going this direction at 4 meters per second squared. Okay, and again, we don't know that it's actually necessarily traveling this way, we just know that it's accelerating in that direction. Okay, so let's grab our equation. Now we've got FR, the subscript there, equals MA. We're trying to find the resultant force, and it's a good idea when you're doing these ones to like list what you know. So I know that the acceleration is 4 and it's in the correct unit. I know that the mass is equal to 20 and it's in the correct unit. And always good to check that. And I'm being asked to find the overall resultant force on this object, which is therefore question mark. If you've got a question mark, what you do when you're doing the algebra, just leave it as what it was in the equation. Okay? And that is going to be a nice straightforward one for you because everything's in the right place, is equal to 20 times 4. Okay? So FR is equal to 80 newtons. And mark scheme wise, you get 1 mark for the formula, 1 mark for the correct substitution of numbers, 1 mark for the numerical answer of 80, and 1 mark for the unit in newtons. The likelihood is this would only be 3 marks, and the newtons will probably be given for you because there's not really much testing in here. All right, good. Okay, so let's up the game a little bit. Okay, so let's do the rearrangement version of this one. let's try an object. No, let's not try a box, okay? Let's try a little triangle. There we go, that'll properly mess with your head. And let's not have it moving left to right, let's have it moving upwards and downwards. Okay, so let's have a force upwards and we'll have a force downwards this time as well. And we'll tell you that the mass of this thing is 250 grams. Right? And we've got an upward force of 70 newtons. And we have a downward force of, what would be nice, 30 newtons. Okay, and what I'm being asked for is I'm asked find the acceleration and state its direction. Okay, so the direction's the easy bit here. Okay, the acceleration will always be in the direction of the larger force. So the acceleration's upwards. Okay, again, not the motion, the acceleration is upwards. And we don't know what that is, so A equals question mark. We need to find what that is. So we know that the mass is equal to 250 grams, and we have a little panic attack because we're, whoa, I've learned my stuff. I've done my revision the night before. Yeah, I've done my revision the months before. All right, I've just brushed up on it the night before, just to be clear. That's 250 grams, and that's a big problem. We need to just change that, and we'll change that into kilograms. Change from grams to kilograms, divide by 1,000, giving you 0.25 kilograms. Right? If you don't know whether to divide by 1,000 or multiply by 1,000, do both and have a look at it. Okay, 250 grams. Is 250 grams equal to 0.25 kilograms, or is 250 grams equal to 250,000 kilograms? And when you look at that, you go, right, with 250 grams, that's less than a kilogram because there's 1,000 grams in a kilogram, so it seems likely that 0.25 is the correct way forward. Okay, because sometimes people get confused in exams as to whether to multiply or divide. Do both, have a look at the answers you get and go, right, which one's most likely to be right here? Now, our next problem then is that we need FR, and we don't have that yet. We've got to go and get that. So remember what we said way back here, that we had the overall force, the resultant force, is equal to total force is one way minus the total force is the other way. All right, so it's either 70 take away 30 or 30 take away 70. Since we already sort of know that the direction's upwards, we're pretty much going to go with 70 take away 30 because nobody likes working with negative numbers if they don't have to. So we'll go this way. Okay, so we'll go, the resultant force is 70 take away 30, which is equal to 40, and that's in newtons, and we're happy with that. And we're being asked for the acceleration. The acceleration is unknown. Okay, now, pro tip here. Start with FR equals MA. All right. Do not rearrange at this stage, okay? Because the marks are for doing the formula. You've got that there. If you write A equals F over M, you still only get 1 mark for the formula. But here's the thing. If you get the rearrangement wrong at this stage, you get 0. If you get the substitution wrong thereafter, you still get 0. Okay? So if you do it like this, you do FR equals MA, 40 equals 0.25A, you've got 2 marks. You haven't done any difficult rearrangements or mathematical things yet, but you've managed to get 2 marks. If you're going to make a mistake now, you've still got 2 marks in the bag. Okay, so we want to find A, we want to get that, we want to get A as the subject of the equation here, so we're going to divide both sides by 0.25. If that's not immediately obvious to you, I suggest you go and have a little look through my videos and look for core math skills, okay, because I did a math skills live stream at the very start of September to kind of get you the basic ideas of how to move equations around and how to get that right. Okay, so dividing both sides by 0.25, 40 divided by 0.25, that's the same as 40 times 4, 160. Don't even attempt to do that in your head in an exam because your brain just goes to mush when it comes to simple calculations. Get your calculator out, press the little buttons, and then at the end of that go, does that make sense? Yeah, it's all right. Okay, and then A is left by itself because that's why we divided by 0.25 in the first place. Okay, so our final answer then is A is equal to 160, and it's meters per second squared. Okay, 160 meters per second squared. So this thing's accelerating pretty heavily. Does that make sense to everybody? I hope so. So with 5 minutes left then, if you're a triple award student or you're a double award higher tier student, so that's basically all of my students, this is the question you're most likely to get. Okay, the most likely question for you to get is what's known as the airplane question. Okay, so we'll even attempt to draw something that vaguely looks like a diagram for this. So let's get ourselves a little runway and an airplane. This could be good. All right, so there is the fuselage. This is not going to go well. I think we've already established that this is not going to go well. What do we need? What shapes do I have? Do I have a semicircle? There's a wing. And there's a cockpit. Okay, we need a wee tail fin and we're in business. Okay, so one airplane. Now our airplane is being affected by air resistance because it's an object traveling quickly through the air, but it is also having some engine stuff going on. Let's assume our airplane has a mass equal to, I don't know what an airplane weighs, let's say it weighs a couple of tons, 2,000 kilograms. It's probably not a fighter jet. 2,000 kilograms, let's give it a forward force of 5,000 newtons. Let's give it a backward force of, I don't know. Let's call it, what do we call it? We call it F for kind of air resistance. We'll not call it little f actually, that would be friction if it was on the ground. We'll call it little r for air resistance. Okay, whoop, pardon me, didn't mean to bring that up. Okay, and let's tell you that this thing is accelerating through the air. And it's accelerating, let's say it's accelerating quite modestly. Let's put A equal to 1.5 meters per second squared. Okay, and you're going to be asked to find R. Okay, what is the backward force in this? And this is where people get super confused because you're like, I've got a force, I've got an acceleration, I've got a mass. What's he actually looking for here? And this is why I laboured at the start that it's FR equals MA. I don't have the resultant force here. If I come over here, remember resultant force, FR, is all the forces one way, take away all the forces the other way. So what am I doing? Well, I know it's accelerating to the right. So I think it's reasonable for me to assume that the 5,000 is a bigger force. It's going to be 5,000 take away R. That's what FR actually will be. All right. M is 2,000 kilograms. And that's okay. We've got the unit right. And A is equal to 1.5. Okay, so let's pop this. Let's substitute all this in here. And now what we should get is a slightly more interesting game. That we have 5,000 take away R, I'll bring this over here because there's a little bit of rearrangement to do here, is equal to the mass, which is 2,000, make that bigger, multiplied by 1.5. Okay, and let's solve the easy bit first. Let's do the math on the other side because we can do 2,000 times 1.5, so that's 5,000 take away R is equal to 3,000. And now I've got to sort this out. Well, my big problem here is I'm dealing with a minus R situation. So I'm going to add R to both sides. Not the only way you can do this, but it's definitely a way to do this. So plus R to both sides. That'll give me 5,000 equals 3,000 plus R. So I need another step here to get R by itself. So I'm going to subtract 3,000 from each side. And the little layout here is quite good where you can tell the examiner what you're doing so they can see what you're planning. All right. So take away 3,000 here and we get 2,000 is equal to R. All right. And let's go up and check this. This is always a good thing to do. Okay, that if this was 2,000 newtons here, what I'd have is I would have 5,000 newtons forward, 2,000 newtons backwards. That would give me a resultant force, FR, equal to 3,000. Is that consistent with the maths that I've got? That would give me the equation FR equals MA. So 3,000 should equal, if I've done this right, should equal 2,000 times 1.5, which it does. Okay, and when you've got that, 20 minutes at the end of the paper because you're super good at physics and you've flown through the paper, come back to this question and check that. It's really common here that when they get to 2,000 here, people start to add on stuff and make this like 7,000 and do weird things. Just check that if your answer to R is correct, if I pop it in there, can I still do FR equals MA and get the right answer with my numbers? Okay, now in the comment section or in the description below, you will there is a shortened Google link. If you click that, you get a little PDF question sheet that's got some kind of nice basic, go and get the resultant force of these, and a couple of questions that ask you to rearrange this, find accelerations, find resultant forces, and then a final question that looks a little bit like this with an even worse diagram than this one. Okay, I hope this has been useful. If this has been sensible and vaguely entertaining for you, can you hit the like button? It really helps me in terms of my ego, which is, as you might imagine, reasonably hard to keep under control. So thank you so much for tuning in this evening. I will see you in 2 weeks' time, and all that's left for me to say is that don't forget, physics rocks. It's true.